Okay, let's continue with part 4 for this class. We have covered phase diagrams, and we are finishing about the TTT diagrams. So we have already seen this isothermal transformation diagram, or TTT diagram, which is for an eutectoid steel. And we have discussed about the importance of thinking about quenching in a straight vertical line rather than using line with a slope. And we said that we'll later discuss about the continuous cooling transformation diagrams, which are the ones for studying that situation. Okay. So some remarks. TTT diagrams help you to determine the microstructure of a steel after isothermal transformations. Not only steels, there are TTT diagrams for other materials, aluminum, copper, but it is more common for the steels. Final microstructure will depart from phase diagrams predictions because in this case, TTT diagrams are made from a quench and then reach an equilibrium at that temperature, but the quenching itself will affect the equilibrium conditions, and so the phase diagram won't apply exactly. For instance, we have a non-equilibrium microstructure, which is martensite, that we can't see traditional phase diagrams, but we are able to see them in these diagrams. So martensite starts to appear at the bottom section when quenching reaches about 100 Celsius. And that's because normally quenching for martensite is made in either water or oil. And you want the quenching to be really fast, so it could be 100 Celsius or sometimes higher than that if you're using oil, but normally we use water in order for martensite to be there. So let's try to see other types of TTT diagrams. This is a diagram for hypoeutectoid steels. What does it mean, hypoeutectoid steels? It means that they have less than the eutectoid composition, so less than 0.77 weight% carbon. So for the this steel has 0.5 weight% carbon, so it's a 1050 steel. It is not only iron and carbon, it will have also some manganese, a little bit of sulfur and phosphorus and things like that, but we call this plain carbon steel, so normally it's mainly steel, mainly iron and carbon, and some impurities, but not really much about it. So we know that we are at the left side of the 0.77 weight% carbon. So these steels will change from 100% austenite into this region, and here we have alpha. So in this region we have a mixture of alpha plus austenite. Remember that this is called primary alpha. And when we are below this, we have either alpha plus cementite, and remember that this is option A of our solving problems on the microstructure, or we might prefer to refer to the Pearlite. So this is Pearlite. So here in the middle, we'll have a mixture of Pearlite plus primary ferrite. So depending on your point of view, you can consider only this possibility, which is ferrite plus cementite, or the right possibility from the engineering point of view. So we'll be talking about Pearlite and primary ferrite. So in this diagram, we can see that. So we can see that above 727 Celsius, which is this temperature, we have what we call the austenite region. You can see this as a new reference, the A3 line. In this case, is just to refer that we are fully into the austenizing temperature. So you can read a little bit more about the A1, A3 lines in other books. I won't explain that in detail, but that's another way for referring to this situation. A1 normally is this temperature. A3 is normally this temperature. So we know that this is 100% austenite. Below A3, we have a mixture of austenite plus primary ferrite. So we said that here, but they didn't mention to you that this is a primary phase or pro-eutectoid phase. Nonetheless, you need to know that, okay? So we can see that if you quench, for instance, to this temperature in the middle of the region, and you wait a certain amount of time, austenite will start to be transformed into the austenite and the primary phase. Notice that you have no end lines. Why? Again, if we draw the line for the Hypoeutectoid steel, if you held your material at this temperature, then you will reach equilibrium. So if you reach equilibrium, you are able to calculate the fractions for each phase. So in this case, this diagram won't help you more than the traditional phase diagram. So wherever you are at these temperatures, you better use the phase diagram. But with the TTT diagram, you can know when transformation will start, information that you don't have in these phase diagrams. In these phase diagrams, these are thermodynamical phase diagrams, so you are assuming equilibrium regardless of how long you have to wait for the equilibrium to happen. So we have these regions between A1 and A3. Below that, now you get into the situation where you are quenching and you are waiting. So we are transforming our material and we cross these two regions. Why is that? Again, if we draw the phase diagram, you have to consider that you are quenching to a certain temperature below the 727 Celsius, but you are crossing this region. So you are quenching, but you are crossing this region. So if quenching happens to be between these temperatures, you will still be able to see a little bit of the primary ferrite. That's why you are crossing and you are forming a little bit of primary ferrite in this region. So if you are quenching to 650 Celsius and you wait for this amount of time, you will see that some primary ferrite will start to appear, to be transformed. If you wait more, then now you will start to form the pearlite, and finally you will have a full transformation. The end result will be the pearlite and the ferrite, the primary ferrite that was formed because of this situation. Now, we know that if we have equilibrium, then we can know the amount of primary phase by using the lever rule, remembering that this is ferrite and this is going to be the region with ferrite, primary ferrite, and pearlite. So this is true only for this region. Below this temperature, you are no longer under equilibrium, so this is not true anymore. So it's not like now we can calculate the amount of ferrite, primary ferrite, using the lever rule because we are away from equilibrium, so we can't use the phase diagram. So in more professional diagrams, they will give you a number here, and that number will tell you the amount of primary phase. We don't have that information in this diagram, unfortunately, but we have another information. So if you are quenching to 600 and you are waiting for this long, yes, we know that we'll have a mixture of ferrite and pearlite. How much ferrite? We don't know. The higher the quenching, the less ferrite you will have. But what we will know is that whatever you have will have a hardness of 23 rho C. Now, if the quenching is more severe and you pass this temperature, now we can see that there is no longer primary ferrite appearing here. So primary ferrite will exist only for quenchings which are lower than this undercooling value. If you have quenches higher than this undercooling value, then the primary phase will no longer exist and you will start to create only pearlite. Now, there is a special name appearing here, bainite. Some people say that bainite is really pearlite, but so fine that you can't longer recognize the lamellar microstructure typical of the eutectoid steels. So remember that pearlite was kind of a lamellar structure. So the lower the undercooling value, the higher the distance between lamellar plates, the higher the undercooling value, the finer the pearlite form. So it's very, very close, one lamellar to the other one. So some people say that when the quench is really severe, you can no longer see these lamellar structures. So it's kind of only seeing something like that. So you really have to go to very, very high magnifications to be able to resolve and see bainite. Now, it will no longer be the nice lamellar structure, so it will be like something like this. So it's very, very different. I'll try to find some microstructure for you to see really bainite. So we can say that above this temperature, you will create pearlite. Below this temperature, you will create bainite. In the middle of these references. You can further elaborate and start to say, well, this should be the line. That's fine. So above this, you have pearlite plus primary ferrite. And below this, you have bainite and no primary phase anymore. And finally, just for the sake of how we use this without this little information, we said that here you have the maximum amounts of primary ferrite, maximum amount, primary, whatever the value is using the lever rule. And here you have the minimum, which is equal to 0. So some guys say, well, this is 100%, this is 0%. So use the proportions rule. So if we are in the middle, you have 50% of that. If you are here, you have 25%, and so on. So that's another way of using it, more complex. But that's one possibility for using it. And finally, if you are quenching really, really fast below this temperature, then you will start to form martensite. And if you are below this line, you will have 100% martensite, at least according to this diagram. For the hypereutectoid steels, we have to remember that now we are on the other side. So this is the 0.77. So now we are going to be creating austenite plus cementite. So the end result, again, although you might use ferrite plus cementite, remember that we prefer to refer to this as pearlite. So we have pearlite plus primary cementite. Okay. This is 727 Celsius. So again, in this region, you prefer to use the phase diagram and the lever rule. Because you will reach equilibrium, but again, you know about the starting point of the transformation. And again, we have a region where the eutectoid austenite or the eutectoid reaction takes place. Again, if you are quenching in this region, you will have the primary phase appearing here, which in this case is primary cementite. And below this, when the undercooling value is very high, the quenching is so far away from equilibrium that there is no longer primary cementite forming. So here you will only have bainite. In this diagram, they don't tell you that. They are using the alpha or ferrite plus cementite, which is okay. But you have to know that you will have really Pearlite plus primary cementite here, and below that, sorry, this shouldn't be there. Below that, you only have bainite. You only have bainite because below this, there is no longer primary cementite. You will only have bainite. Okay? And again, your lines for the starting of the martensitic transformation, and this is for about the end. This is 90% transformation, so some people say that, well, the end is there. In real life, might be even lower than that. It could be in the minus Celsius region, but that's another story. So for the plain carbon steel, you can see that at 1045 steel, you have this hypoeutectoid situation. So you have the traditional starting and end lines. But if we add some alloying elements, in this particular case, the 4340 steel, you can check that in your software or your computer, you will have more manganese in this alloy. So by adding manganese and other things, there is a change in the shape of the graph. So you can see that the starting of the transformation at 650 without alloying was a few seconds, less than 1 second. But now that you are adding manganese, transformation starts at maybe 300 seconds. So from 1 to 300. That's a really big change. So by adding other elements to your steel, you can control how fast transformation takes place. And that's fortunate because when you are trying to develop a microstructure in a material, if your material is very thick, heat transfer in the center of your material will result in a very high temperature compared with the temperature for the surface. So when you are quenching a part that is very thick, the microstructure will change a lot from the surface to the center because the time for it to change temperature is very different. So by alloying with manganese, silicon, and other elements, you can give more time for the material before transformation takes place. So you can isothermally held your material. Like let's say that you are quenching for this temperature and you are waiting for very long time. So once you have all your material, the center of your material and the surface to the same temperature, now you can quench and have a 100% martensitic structure rather than in this case. So if you are trying to get a 100% martensitic structure in this material, you have to quench the same way as here. But because your material is very thick, it happens that the center isn't following this graph. The center is more like doing something like this. So perhaps the center of your material will not have 100% martensite. It will have maybe 50% martensite and 50% a different material. So when you are alloying a material, you want to control the way it transforms. So TTT diagrams are used for predicting microstructures after different quenching operations or sequences. So you can heat treat steel by quenching it, and by quenching it you can control how much of different phases you are creating in your material. So you should keep in mind that austenite is the only phase that can be transformed. So if you have already transformed 50% of your material into perlite, the other 50% remains austenite. So if you further quench that for the martensitic temperature, so the 50% of perlite that you have already created, it won't change anymore. So that will prevail after the quenching, for the quenching. But the 50% austenite that it is still in your material, that 50% will be the only one that will be able to transform into martensite or whatever the new temperature of quenching is required. So in heat treatments, where you have different quenchings, every quench is as a separate problem, but the only phase that can be transformed is austenite. So in every step, you have to subtract the austenite that has already been transformed, and you are left with less austenite for transformation to happen. So we'll see a few examples in a moment. So let's have a break now, and after the break, we'll see some examples of using the TTT diagrams.